presentation. Of note, we have other collaborators from the Texas A&M University Process Safety Center. So to the extent that there are detailed process safety questions, we'll probably have to refer you to our colleagues for some of them. But we'll start with kind of an overview of how this fits in. And maybe as a bit of context, many of you have probably looked at or are participating in the, what is it called? Driving to Zero, or the goal being, can we get to zero methane emissions in the same way that we've set our sights on zero safety incidents, where at some point decades ago, the industry said, personnel safety is a top priority, and we're not going to accept our people being hurt or killed. And so we are going to develop systematic processes to eliminate those occurrences and mitigate the effects of other unintended events in our process to make sure that we're protective of people. And there has been, across my entire career, a lot of discussion around treating environmental incidences in the same way that we treat process safety, that we're going to collaborate, that we're going to be systematic, that we're going to identify ways to engineer out these types of events. And the good news is there exist systematic approaches to doing just that. So today we'll review how that is approached within the process safety framework, and then describe how it fits into eliminating some of the emissions events that we're most interested in abating. Often, whenever we start, we use this adapted 2x2 illustration, adapted from a Daniel Zavala article a number of years ago. Looking at, on the left, routine sources of emissions. These are the things that we engineer into our processes, whether they be blowdowns to the atmosphere, liquid unloading. We know we have pneumatic controllers that vent methane and other hydrocarbons, or on the right, unintended emissions. We've outlined 3 of these quadrants in red, because these are the emission sources that in aggregate appear to be well represented in emissions inventories. Some of them are overestimated, some of them are underestimated, but the large discrepancy over the last decade or so that has come between atmospheric observations and our bottom-up inventories is often hypothesized to really be related to the large unintended emissions that are factually observed in the field and throughout emissions data. And so if we think about how we are estimating, quantitatively predicting, and planning abatement for the routine or the small unintended emissions, we have a lot of advanced progress against that. We have both deterministic as well as stochastic emissions models, depending upon the source, that represent these pretty well, and they are systematically included in emissions inventories. However, this large unintended emissions category, which are the things when we see tanks that are open that we didn't anticipate to be open, or flares that aren't lit, or other large emission sources that aren't well characterized, these have been limited to empirical observations. And so when we see these large field studies that attempt to take these observations and extrapolate them and try and produce inventories, that gets us part of the way, but that's not always as insightful for designing mitigation strategies. And so it becomes really important to think about how we can quantitatively incorporate these types of emission sources in a way that will enable mitigation as well. And so the good news is this is a well described discipline of engineering already. And so I'll just walk you through this bow tie diagram to discuss how this process generally starts. These are activities I've participated in myself, working in different operational contexts. And so generally, this type of activity, maybe it's called a HAZOP or a HAZWOPer or something that has to do with evaluating hazards that could lead to either process safety or personnel safety incidences. So a top event is identified, the thing that an interdisciplinary group of engineers and scientists are going to think about being worried about. So for example, if we were going to analyze hazards associated with driving a car, we might say the thing we're really worried about is the case where we lose control of our vehicle for whatever reason. And then we would sit down as an interdisciplinary group and think about all the threats or things that could lead to a loss of control of a car. And some of them might be user error. It could be the driver becomes distracted or the driver just makes an error of some sort. It could be that there are hazards in the road that are either anticipatable or not. It could be other things that are completely outside of the control of the vehicle operator, such as other drivers. And so we can systematically identify all of those and think about those things lead to the top event, which is a loss of control of the vehicle. And the consequence that we're really worried about in a loss of control of a vehicle is usually death or injury of the driver or the passengers of the vehicle. And secondarily, financial damage to the vehicle, or that your vehicle can cause something else. And so these things are pretty intuitive. And then the next step is to think about what are the things that we might use to prevent the thing we don't want to happen. So let's take a case where our threat is a wet road. We're driving a wet road and we are worried about, we encounter something, we need to stop short, you slam on your brakes. 20, 30 years ago, people were taught if you slam on your brakes, then your brakes will lock up, your wheels will lock up, and maybe you'll slide instead of stopping. So then the general community introduced an administrative control. They said, okay, we're going to teach everyone not to slam on your brakes. Everyone needs to learn to pump their brakes so that their wheels don't lock up. And then eventually there was an engineering solution, and every car I think that's made today includes an automatic braking system that automatically pumps your brakes and prevents it from locking up. So you can see how you can introduce systematic either administrative controls or engineering controls that prevent the thing that you're worried about, the loss of control of your vehicle, from occurring. The other element that can be introduced are mitigative barriers. We know that the preventative barriers aren't foolproof, or maybe we haven't thought of everything. They only have some probability of being protective. So to the extent we lose control of our vehicle, but we still don't want to maim or kill drivers or passengers, what else can we do? Now we can introduce things that are going to minimize the consequence of the top event. So we lose control of our vehicle, but we have seat belts, we have airbags, we have roll cages in vehicles that are prone to rolling. And in that way, we can minimize the bad thing that happens as a result of the loss of control of our vehicle. And so this is systematized across all types of industrial processes, chemical plants, petrochemical refineries, upstream. And I would be loath to discover that there's a single company out there that doesn't have these types of analyses when it comes to process and personnel safety already in place. And you'll see, for example, we already have things like pressure relief devices on equipment that could experience pressures that exceed its pressure rating, because we're already worried about not blowing up equipment, not harming people, and the like. Unfortunately, historically, the types of emission sources that continue to remain that are kind of prevalent, so the open tanks, the unlit flares, things of this nature, are not always the same as something that would lead to a significant safety consequence. And so often those scenarios are tossed out because they don't meet the criteria of creating a consequence that we're worried about. So for example, if you have a bunch of gas go to a tank, but you have an exit for that gas, you have pressure relief devices, you have a thief hatch or something like that that can open, then you will have prevented the tank from blowing up. And that's the thing that you're worried about. And unless you have toxic gases like H2S, generally the tanks are tall, they're away from people, they're not in confined spaces. And so there's a negligible safety implication for that event. But we know from an environmental perspective that a little bit of emissions, that an emissions relevant concentration of gas is really different than a safety relevant concentration of gas. Just because it won't catch on fire doesn't mean it's not a problem. And so here the hypothesis is that if we can bring back in these particular events and incorporate them into the types of analyses that companies are already familiar with, and have a clear definition of, in addition to tier 1 and tier 2 process safety incidences, we also have a clear super emitter type set of definitions that can be incorporated. Then the same types of approaches, the existing expertise, can be used to mitigate large emissions, large unintended emissions. So I'll walk you through a quick example applied to a really simple site. So let's consider the case where we have a dry gas well. You have a wellhead producing gas and water as a general matter. And so the process is you produce gas and water out of this wellhead. It flows into a separator. That separator separates the liquid from the gas. The gas goes to some sort of sales line. The liquid accrues in the separator until it's dumped out into a water tank, which will be emptied in some other way at some other time. Maybe trucking, maybe some sort of other means, but we'll just say that's the end of our process for this discussion. As I already mentioned, people have thought about the safety consequences. What happens if you overpressure this tank, if you overpressure this separator? So there are pressure relief devices and the like on this equipment to avoid that explosion or that fire. But what we don't necessarily have engineered in is the cases that prevent the super emitter consequences through those pressure relief devices, because that wasn't a safety scenario. And so we can construct similarly a bow tie diagram sitting around a room thinking about what is it we're worried about? We're worried about excess gas, for example, making it to that tank. Because if the excess gas makes it to the tank has a pressure rating that's less than 1 pound. Maybe it's 8 ounces, maybe it's 16 ounces at the maximum. But any more gas occurring in that tank, the thief hatch is going to open or the pressure relief device is going to open and the gas is going to go into the atmosphere, which we would observe in a flyover or something like that as gas coming out of a tank. So the types of threats that might create that situation could be things like that dump valve, which is used to empty that separator episodically as the water accrues in the separator and move it to the tank. That can become stuck open. If that becomes stuck open, then the full volume from the well goes directly to the tank, including all of that gas. Or you could have some sort of problem with the controller that's operating that dump valve, in which case maybe your separator is not working correctly and you have extra gas going over to the tank. Or maybe you have the type of process that is referred to as a manual liquid unloading. And that is, as gas wells mature, there's a scenario where liquid kind of plugs up, if you will, the subsurface casing and the gas stops producing. And so the simplest or most manual way to address that is to shut the well in, let it build up some pressure, then bypassing the separator directly to the tank, open it back up and let that built up pressure kind of burp that water into the tank so that you can clear that line and then route back to the separator and resume that process. It was observed a number of years ago that operators were shutting in the well, going about their business, coming back when it was pressured up, opening it back, going about their business, and then coming back later to reroute through the separator. And so that was observed as creating extra emissions associated with this process. So now if we think about how do we prevent excess gas carryover to the tank, considering this liquid unloading, we can think conceptually about if you have an operator and say it takes 30 minutes for that water to clear from the time you open the wellhead, bypassing the separator back to the tank. But you open that valve and then you leave for 5 hours because you're going about your business because you don't have 30 minutes to sit on that side or an hour to sit on that side and wait for that line to clear. Then you have an extra, in that case, 4.5 hours of all the full wellhead going directly to the tank. And so that's what we're describing as a prolonged manual liquid unloading. And what you also might remember is, goodness, maybe 7 years ago now, operators started coming out and saying, the 3 things you need to do right away if you want to mitigate emissions are change out your high bleed pneumatic controllers, man your liquid unloadings, meaning the operator should stay put and wait for that 30 minutes so that as soon as the line is cleared, you can shut it back in and go route through the separator again, and inspect your components for leaks. So those were the big three things to go do. And we saw a lot of emissions abated on account of that administrative practice being introduced into the manual liquid unloading. So first we can say, have an operator just stay there and minimize the amount of time that the well volume is flowing directly to the tank. And so by reducing that from 5 hours to half an hour, you should reduce the incidence you observe over a population of well sites, if you're doing a flyover of some sort, by an order of magnitude. Now, maybe we've moved from the administrative control of stay put, like pumping your brakes. Now we have an engineering solution. We're going to use some sort of automated lift system. We're going to clear that line on an automated basis. We're not going to rely on a person to do it correctly, which would have two implications. First, it is not limited to the time of day where operators are performing their rounds. And so now these events are being spread out across 24 hours a day. And the amount of time that the well is left open to the tank is minimized. And as a result, you would further expect to see from some sort of flyover surveillance data a further reduction in the incidence of observations of emissions coming out of the tank that were attributable to liquid unloadings being too long. We can also consider the stuck dump valve, where we would similarly observe emissions coming out of the tank. And if you're just flying over, what you don't know, kind of going back to earlier describing that just observational extrapolation to emission inventories is less helpful for mitigation, you don't know if when you observe emissions coming out of this tank, if it's because there's someone on the ground that has a prolonged liquid unloading going on, or maybe a dump valve is stuck open, where instead of that dump valve discreetly emptying a separator like you would flush a toilet, instead it just stays open and it keeps running and running and running, and all the fluids are moving into the tank. All you're observing from the airplane is gas coming out of that tank. But we can also consider the case where a dump valve is stuck open, and there's a fair bit of data that helps us understand the likelihood of this, because it's also an issue for reliability. And we can consider then constructing an entire bow tie diagram, thinking about with a stuck dump valve, we can maintain it, and that might improve or prevent the outcome of it being stuck open and creating our unintended consequence. We might install some sort of meter to monitor for that condition to allow us to respond to it quicker. So systematically, we can go through. We can also consider mitigative barriers. So not only can we try and reduce the likelihood that this thing happens in the first place, but then much like a seatbelt or an airbag, we can try and minimize the amount of emissions associated with the condition of excess gas going to the tank. And so we might install a vapor recovery unit, we might install a flare system so that at least if gas goes to the tank, it's burned instead of vented. We might have some sort of throttling system where we automatically shut in a well. Sometimes these things work together, and so they have to be considered. But once you start to build these things together and think about discrete barriers and discrete threats, you can begin to quantitatively consider what additional barriers you can introduce to systematically reduce the risk of your top event and the magnitude of a consequence in the case that you do have this top event or the bad thing that you don't want to occur. So the place we all want to get to is the point where we can predict and then prevent these types of incidents. So it's great to be able to map it, and that'll be really helpful in our view to be able to fill in that last quadrant more systematically when it comes to developing emissions inventories that meaningfully and quantitatively include the excess emissions or large unintended emission events. But ideally, we would predict and prevent them so that they don't occur in the first place. And so through this, we can start to quantify the failure rates of the equipment that are involved in the threats that lead to the top event. This is a well-defined discipline within reliability and process safety, and there are already a number of equations and data sources and a large mass of published literature that to the safety community is much like our emissions literature to the environmental community. And so we can leverage this through the collaboration with our colleagues that focus on this discipline, and notice that the same equipment that you're worried about failing that could lead to a process safety incident is the same equipment you're worried about failing that would lead to an emissions event. So for example, if you're worried about a dump valve getting stuck open, because that also has significant implications for the reliability of your process, you're still trying to sell that gas, for example. So then the reliability of dump valves have been studied for various applications. And now we just need to bring these two worlds together in a meaningful way. And so let me just talk briefly about how we characterize failure rates. Generally, they're characterized by what we call a bathtub curve. This will also probably be really intuitive to you. At the beginning, when equipment is manufactured, some small percentage of it is going to be defective. So if we go back to the car example, everyone's heard of a lemon when you buy a car and it's new and it really shouldn't be breaking down as if it had 300,000 miles on it, but it just keeps breaking. So you kind of have your lemons from equipment that's being produced. And so manufacturing defects or design defects, there are some types of equipment that before they even really have a lifetime break down a lot. But things that survive that kind of burn-in rate that are functioning normally have some frequency of failure, but it's pretty stable. So again, you can think about your car. It's kind of like that first 100,000, maybe if you drive a Honda or a Toyota, first 200,000 miles, stuff breaks from time to time. There are some things that break down, but as a general matter, you turn on your car, it starts, and it's pretty infrequent that you're going to have a major problem. But then at the end of life, now you're to that clunker phase and stuff just starts to break down all the time. And at a certain point, you just see this failure rate, the failure of your car in this case, just increasing substantially, that it becomes, you start having the conversation with yourself about maybe it's worth just replacing. This thing is breaking too often. So similarly, we can characterize the failure of individual components in a way like that. And what's important to know is that each component has its own distinct bathtub curve. And often in the literature, when we're describing failure rates, it's often focused in this useful life region. So we're going to have a kind of population-based, steady state description of the failure rate. And so, as I mentioned before, setting aside without burn-in rate, there's a variety of literature and available data describing the failure rates and what happens at the end of life of a piece of equipment for the individual components. For pneumatic control valves, I will flag for you that this is generally the pneumatic controller's ability to perform its function as opposed to the pneumatic controller's ability to not have extra emissions. So you have to be a little bit careful, but what is the likelihood that your pressure relief device is going to perform its function as you expect? What about your other safety instrumented systems? And you can then begin to construct the probability and combined probabilities of failure across a system. And what are the likelihoods or the expected frequencies that you would begin to see these top events based upon the various threats that have been identified. And so we can go back to our bow tie diagram and begin to quantitatively construct a fault tree. And so this is the type of analysis that's performed. You can start to think about, what if we want to know the likelihood of excess gas carryover to a tank attributable to manual liquid loading, unloading process failure, whether that be some sort of operator error or some other sort of mechanical error. What if it's also a system might be automated versus manual? Or what if we're also worried about combining the case where the separator dump valve is stuck open, and we can systematically describe these and which things have to happen at the same time and which things are an or function to quantitatively estimate how frequently we would expect excess carryover to a tank for a particular system design. These numbers are preliminary from our first pass at beginning to construct these fault trees for a particular oil and gas system, but you would expect, based upon the varying configurations of these systems, we know we see it. So if we had come to the conclusion that you should only see this once in 1,000 years, we would know that was inaccurate. And so this is how we can start to match our observations. How often do we in fact see gas coming out of that tank as an indication of whether or not we've described these probabilities accurately in aggregate? And so you can do the same sort of thing that with the preventative barriers as well as the mitigation barriers. We can also think about, well, what if we add a vapor recovery unit? What if we add a flare, a flare to our system? And we know that there's only some amount of a mitigation that comes from a flare. There's only some amount of mitigation that comes from a vapor recovery unit, because those individual pieces of equipment also have some reliability data associated with them. And then we also can evaluate the cost of any of these barriers, whether they be preventative or mitigative, and start to think about this on the basis of reducing the risk of our unintended consequence, our super emitter event, our large emission event, for a given cost, and optimize the system to bring that likelihood of having an unintended emission event brought into an acceptable risk for a given cost and optimize around that. Exactly how process safety and personnel safety is handled. And from there, I will pass it over to Dave to describe bringing those concepts together with a real life use case that we think you'll be really interested in, that Colette's also been working with us on. And so take it away, Dave.
Thanks. So what Erin's been talking about is applying this process safety analysis framework to develop bottom-up approaches rather than top-down approaches to looking at, can go back, to develop bottom-up estimates of the probabilities of these threats and the effectiveness of various types of barriers, either preventive barriers or mitigative barriers for these large emission events. What we need to do broadly is to then compare what this bottom-up approach, based on these probabilities of various types of events from fault tree analyses, give us compared to what we're seeing in the observational data, and begin to develop robust estimates of what these bottom-up estimates would be based on various facility designs. But there are other applications of this as well. Up until now, we've been talking just about a single site, a single facility. We also make the argument that you need to be looking at supply chains and applying the same framework to supply chains. So let's now go to the next slide. And so imagine now that we're in our supply chain and we have not an individual site threat that leads to a top event, but we have a supply chain threat. So imagine a disruption to a gathering and boosting line, or a disruption to a transmission line that would then cascade back upstream and potentially downstream through the entire system, causing events at individual sites. So for example, there might be overpressure events extending back up to production sites. There might be pipeline flow interruption extending to all points in the supply chain. And other types of shutdowns. So we also need to be thinking about these types of threats and looking at them to quantify what emissions associated with these types of malfunctions might be and how we could prevent those. So anecdotally, we decided, we have been hearing a lot about certain types of supply chain disruptions with various types of consequences associated with them. So we decided to look at a particular case study just to say, how big could these supply chain threats be? So let's go to the next slide. So what we wanted to do is look at a relatively simple case study. We've done some very preliminary work on this, looking at the frequency of supply chain disruption that could lead to emissions and flaring at upstream facilities. So imagine that you're operating an upstream facility and you have some sort of disruption, either in a gathering boosting line or transmission line, or something else happens that affects the supply chain, but there's now nowhere for the gas to go, or you're seeing increased pressure in the lines leaving the production site. These disruptions anecdotally might last hours to days, and if they occur, they would occur not at a single site, but they would occur at multiple upstream sites that would be spatially correlated, that would appear at the same time in the same location. So can we go to observational data and assess whether or not that's occurring? So that's what we tried to do with some results that we'll present to you here. So let's go to the next slide. So we looked at flaring in the Eagle Ford, and the last slide that you were looking at was locations of flares identified by the VIIRS night fire data product in the Eagle Ford production region in South Central Texas. And if you look, as Colette Chassel did, at all the flare clusters identified by VIIRS in the Eagle Ford, what you see is that the vast majority of the flares aren't processing gas very often. The median value for the detection frequency by VIIRS of a given flare. So VIIRS has previously detected a flare in a location. How frequently on the daily overpasses where they have good observational conditions can they see the flare lit is only about 6% is the median value, an average value of 11% in the Eagle Ford. So most flares are not on very frequently. And so if flaring activity is due to top events occurring at single facilities, leading to things that might cause flaring or increased emissions, then we would expect no spatial and temporal correlation necessarily between these nearby flares. We would expect that they would be independent, and the probability that you see a nearby flare going off if you have a flare ignited at your facility would be very low. And so is that in fact the case? Is that what's observed? So that's what we wanted to look at. We looked at the case study of the Eagle Ford. So yeah, let's go to the next slide. So if you look at all the flares and all the flare clusters detected by VIIRS across the Eagle Ford, what you see is the average number of flares emitting at any given time in the Eagle Ford shale is about 42, given that we have a flare ignited. So pick a flare. What's the expected value of the number of flares throughout the rest of the Eagle Ford ignited at the time your flare is ignited? And about 9% are ignited. Now ask, well, how many of my neighbors' flares are ignited? What fraction of my neighbors' flares are ignited? And how does that compare to what I would expect if the result were random, were based on independent facilities, not tied together in some way, presumably through a supply chain? All right. Then we look at how many flares on average are there within a 5-kilometer distance of any given flare. On average, about 4. What's the average number of them that are lit? If my flare is lit, 1.5, 1.6. So roughly 44%. So much more common for nearby flares all to be ignited at the same time. So let's take another look at this and apply it a bit more quantitatively. So let's go to the next slide. We're missing one. And that's one I really want to show. So I'm going to pull up that slide. And I'm going to show it. And so if you let me share, Aaron, right? So I'm now going to go full screen. So what Colette did was to go and look at all these flares in the Eagle Ford and just looked at those flares that were infrequently detected. There were a small number of flares that accounted for about half of the emissions. And the flares that were relatively infrequently detected, in other words, less than about 18% detection frequency. So if we have infrequently detected flares, and we looked at those flares and asked what fraction of them had nearby flares lit when that infrequently lit flare was active. 87% of those inactive flares had at least 80%, 80 to 100% of their detections that we classified as multi-site events, flares lit nearby. These infrequently lit flares account for about half of the flaring in the Eagle Ford Shale. And so in the Eagle Ford Shale, it appears that some sort of top event that is causing a supply chain disruption is leading to localized, more frequent flaring. And so we take this as an example of we need a bow tie diagram. We need to identify all these threats, right, that lead to this top event of flaring occurring in a localized area because it's leading to an enhancement of flaring in the Eagle Ford, and we suspect in certain other basins. And so this gives us a framework to begin thinking about a supply chain related example to this type of analysis. We'd be delighted to hear what your ideas are on what the threats are that might cause these types of supply chain disruptions. We've offered up some examples, but be delighted to hear what your examples are. But broadly, what we've been trying to communicate today, and then we'll turn to questions, is how do we begin to develop the same sort of systemic predictive methods for these unintended emissions and large events that our community has discovered are so important to understanding total emissions from oil and gas facilities? And then how do we structure a framework that allows us to rationally build preventive and mitigative barriers to these types of emission events? So with that, we'll open it up for questions, and I'm going to now stop sharing my screen and look forward to your questions.
Yeah, thank you, Dr. Allen and Dr. Telos. Yeah, thank you for presenting. And if anyone has any questions, just raise your hand or feel free to pop it in the chat. And Thomas, looks like you have our first question.
Thank you. Thank you for the presentation. I have a question regarding the human side of this and cultural aspects of oil and gas production. So obviously in the last many decades, we've had a very big shift in the oil and gas industry towards a culture of safety, and this is percolated throughout the culture of operators. But culture is pretty slow to change. And people will follow protocols related to health and safety